We're going to find the volume of some very fun shapes today. All right, so what we're going to do is we're going to take a rectangle or we're going to take a whole region in a plane and we're going to revolve it around a line. And this is called a solid of revolution. You're basically revolving a two-dimensional figure around a line, and it's going to create a three-dimensional figure. And the line is called the axis of revolution. So whatever you're revolving around, that's called the axis of revolution. The simplest such solid is a right circular cylinder or a disk, which is formed by revolving a rectangle about an axis adjacent to one of the sides of the rectangle. So we're going to rotate this rectangle around that axis right there. And when we do that, it's going to create a disk. All right, what would the volume of this disk be? How do you find the volume of a cylinder? Area of the base, okay, which would be pi r squared. They've labeled the radius as big R in this picture. And then the height of the disk would be what? W. Good. Okay, so the volume of that disk is pi r squared W. All right, now let's picture taking this whole region right here and revolving that around the axis of revolution, which is right here. So what we want to do is we want to think of it like kind of like the cross sections that we've been talking about, but we're going to take one rectangle and we're going to let the height of that rectangle be r, because we're dealing with a circle here when we revolve it. So we're going to take the height of that rectangle, and that's going to be r. And then we want to figure out what the volume is when I take an infinite number of rectangles whose widths become 0. So basically, the width of the rectangle becomes dx. So does anyone have an idea of what that formula would be? The integral, very good, of, okay, the top minus the bottom, which we're going to call that r for the time being. All right, well, basically all I'm doing is I'm taking a bunch of these rectangles up here, but I'm taking an infinite number of rectangles whose widths are approaching 0. So that width just becomes my dx. Yeah, so it's just pi r squared dx. Okay? So the volume, when I take that two-dimensional figure and I revolve it around that axis of revolution, the volume is going to be the integral of pi r squared. And I would integrate it from, is that a to b on your paper? And then I just kind of I copied some pictures of what that figure would actually look like when you revolve that original two-dimensional figure around the axis of revolution. So this is the entire figure, and then this right here is basically just kind of a representation of a bunch of those rectangles. But keep in mind that we're doing an infinite number of rectangles whose widths are approaching 0, and that's what the integration part is. Okay, so if you look down to the box right below that, it gives you basically a general formula for finding a volume. I put r of x here as the radius, but basically that r of x is just saying we're talking about the radius, but those formulas are in terms of x. And the length of that radius is still going to be the top minus the bottom curve. And I pulled the pi out in front because I kind of like for the coefficients to be out in front. Now, that's if you're rotating around a horizontal axis of revolution. If you're rotating around a vertical axis of revolution, then the length of r is going to be the right side minus the left side, and the thickness would be dy, so you're having to integrate with respect to y. Okay, so those are just basically the two basic formulas. Don't freak out. We're going to work some examples, and it'll all make sense. Note that you can determine the variable of integration by placing a representative rectangle perpendicular to the axis of revolution. Okay, that's what's key here, is that that rectangle that you're revolving has to be perpendicular to the axis of revolution to use this formula. If the width of that rectangle is dx, you're integrating with respect to x. If the width is dy, you're integrating with respect to y. All right, find the volume of the solid formed by revolving the region bounded by the graph of f of x equals root sine x and the x-axis between 0 and pi about the x-axis. Well, if you were to graph this on your calculator, the square root of sine x is going to look like this. Forever and ever and ever. But we just want the area that's bounded by that graph, the x-axis, and between 0 and pi. And the easiest thing to do is on your calculator, set your window between 0 and pi. And when you do that, that's where your window is right there. So what we're really doing is we're revolving this semicircle type figure around the x-axis. And some things we're going to be revolving around the x-axis, some things we're going to be revolving around the y-axis, some things we're going to be revolving around another horizontal or vertical line. So I think it's helpful to draw this little arrow to indicate what you're rotating around. All right, so R is basically, so there's your rectangle right there. The width would be dx, so therefore R is going to be the top minus the bottom. All right, so what would the length of big R be? Yeah, it's just the square root of sine x, technically minus 0. The top of that rectangle is the curve square root of sine x. The bottom is y equals 0. All right, so the formula is going to be pi integral of R squared Can you picture, if you revolve kind of the semicircle around the, which is not exactly a semicircle, what shape would that be after you revolve it? Yeah, it's kind of a sphere. It may be more like an egg, but it's kind of a sphere type thing. So the radius of that sphere is going to be from basically the top of the curve to the axis of revolution. Yeah, the radius is going to be the same thing as S that we were finding, and it's going to be top minus bottom. So if you type that into your calculator, then you should get 2 pi. Does everybody feel confident that you could type that into your calculator and get 2 pi? You could actually do that one fairly easily without a calculator also, because when you take the square root of sine x and square it, what do you get? Sine x. And the integral of sine x is negative cosine x. If you just take the rectangle that I drew on here and revolve it around the x-axis, that would be a disk. But what the integral does is it takes all of these rectangles and adds them together to get the volume. Okay, so that's it. Your answer is 2 pi. There was a lot of room on that problem that you didn't really need. All right, find the volume of the solid formed by revolving the region bounded by f of x equals 2 minus x squared and g of x equals 1 about the line y equals 1. All right, draw the area that's bounded by these graphs first. Okay, and then what are we revolving around? The line y equals 1. Okay, so this is not really any different than what we just did, but I've just kind of shifted it up. The only thing that's going to change here, and remember that my rectangle needs to be perpendicular to my axis of revolution, and therefore the width is going to be dx. R is basically the height of that rectangle. So what will the length of R be? Good. 2 minus x squared minus 1. There's a trend here of the length of your rectangle always being the top curve minus the bottom curve. And if you want to simplify that, it would be 1 minus x squared. All right, so that volume is pi integral of r squared and what will the limits of integration be? -1 to +1. Good. All right, that ends up being 16 pi over 15. And once again, you get kind of an egg shape here when you revolve that. All right, up until now, that radius, or the figure that we're revolving, has butted up against that axis of revolution. So it's created a solid figure throughout the whole thing. But we can also take a figure and revolve it around another axis that's, say, a little bit above or a little bit below that figure. So picture this rectangle right here that's shaded, and we're going to revolve it around that line right there. So when you do that, instead of getting a solid disk, you're going to get what's called a washer. A washer has a hole in the middle of it. So if I wanted to find the volume of this washer, r is the distance from the axis to the top of the figure, big R. Little r is basically the radius of what? The hole. Good. And then W is still our height of that washer. So what would the volume of that washer be? Or what's a general method for finding the volume? Good. All of it minus the hole. So the outer volume, if it didn't have a hole in it, that outer volume would be pi r squared, pi big R squared W. Everybody okay with that? And then what would the volume of the hole be? Pi little r squared times W. All right, so if you wanted to, we could factor out a pi and a W and then get big R squared minus little r squared. All right, but if that thickness or that height of that washer, if we want to take a bunch of washers and make an infinite number of revolutions with rectangles and then make the width of those rectangles approach 0, then that W is going to become a dx. So you would be integrating pi big R squared minus little r squared dx. Okay. So basically I've just transformed this formula into big R squared, and it's in terms of x, minus little r squared. You're integrating it. Make sure you get your pi in there, and you're integrating from A to B. All right. Find the volume of the solid formed by revolving the region bounded by the graph of y equals root x and y equals x squared about the x-axis. All right. I'm fairly confident that you could do this on your calculator, so I'm going to graph it for you. Okay, so the part that's bounded, that's x squared, and that's root x. And we're trying to revolve it around the x-axis. Okay, now remember that your rectangle has to be perpendicular to your axis of revolution. So we're going to stick the rectangle right there, and that's dx. Your first job is to determine when you revolve that figure, are you going to have a hole in the middle, or is it going to be a completely solid figure? Okay, there will definitely be a hole in the middle of this one right here. So if there's going to be a hole, then you have to use the washer method. So we're going to do pi integral of big R squared minus little r squared. No, the hole does not have to extend all the way through the object, because right here, basically right here, you're not going to have a hole right at the origin.